Okay, welcome to day 3, solving equations that involve trigonometry. So we're going to look at equations that have trig functions in them like sine and cosine, and we're going to solve for x or theta or whatever the variable is. Going back to our unit circle, so when we solve, it's not really using inverse trigonometry. It's about what we did on that homework 28 when sometimes we get multiple solutions for the angle theta based on the unit circle. So here's my quadrant 1 of the unit circle, which you should know. Tangent is sine over cosine, or the slope, and I'm going to put those in red. So the slope here is 0, the slope here in the middle is 1, the slope here at the top is undefined. This one is 1 over radical 3, which is equal to radical 3 over 3, and the slope here is radical 3. All the x, y values are the sines and cosines, and when I have cosecant, secant, or cotangent, they are the reciprocals of the sine, cosine, and tangent functions. I know all students take calculus. That's going to help me when I start solving based on if I have a positive or a negative result. And if you look at quadrant 1, all these angles are pi over d, and all the other quadrants are always going to be n times pi over d, where in quadrant 2 the numerator is 1 less than the denominator, in quadrant 3 the numerator is 1 more than the denominator, in quadrant 4 the numerator is 2 times the denominator minus 1. And that's all we're going to look at. This is how we're going to solve equations. Now, when we solve, there are many results that I could do. Okay, so we're going to solve equations, and our result is going to be radians only, so our solutions are going to be angles. And we're only going to solve it on one unit circle. Kind of what we did before on that preview homework. So when I see this first problem, I see a lot of trig going on here, but I really look carefully and I say it looks very similar to what I have over here. They basically look very much the same. Okay, cosine times sine minus cosine, it looks like 2xy minus y. And the idea is that I want to factor things. I want to see what is in common. How can I make it easier on myself? Well, what do I see in common? There's an x in both of these terms. So I take a x out, I have 2y minus 1 is equal to 0. And I can solve. I can set this equal to 0. I can set this equal to 0. And when I set things equal to 0, well, I already have x equals 0. And I set this equal to 0. And I add 1 divided by 2. I get y equals a half. So I have a couple solutions here. And that's what's going to happen. We're going to get multiple solutions to what we're doing. So for the very first problem, what do I see in common? I see a cosine of x in common. And what would be left inside of the parentheses? 2 sine of x minus 1. Don't forget the minus 1. So how do I solve this? I set this guy equal to 0. I set that guy equal to 0. I get cosine of x is equal to 0. And I have 2 sine of x minus 1 is equal to 0. Add 1 divided by 2. I get sine of x is equal to a half. So now what am I doing? I'm solving for angles. What angles does this happen on this unit circle? Well, cosine of x is equal to 0. Or what angles do I have to be at? I'm at pi over 2 and 3 pi over 2 as my angles. And when does sine of x equals a half? Well, this is when x is equal to, well, positive, quadrant 1, pi over 6. And positive sine is in quadrant 2, 5 pi over 6. So I may make some notes here, because this is what I like radians so much better. Yes, this is in quadrant 1, this is in quadrant 2. But look, I have double solutions. I have 2 solutions for each part that I did here. okay, one for the cosine part and one for the sine part. Each of them had double solutions, and they have the same denominator for each. Yeah, the cosine part and sine had different denominators, but my two solutions for the sine part were something over 6. My two solutions for the cosine part was something over 2. This is the way these double solutions are going to work. You can't get a double solution using sine and get one of them be a something over 6 and something being a something over 4. That's never going to happen. This is why I like radians better. It really turns out to be much, much easier. Again, what do they have in common? Tangent of x. I take tangent of x out. And what's left inside? Radical 2 cosine of x. Don't forget your minus 1. I can set this equal to 0. I'm going to add 1 divided by radical 2. And 1 over radical 2 is the same thing as radical 2 over 2. And then I set this one equal to 0. Tangent of x is equal to 0. And now I can solve for the angles. When does tangent or my slope is equal to 0? When I'm at 0 radians and when I'm at pi radian, both times the x-axis. Still the same denominators. And when is cosine equal to radical 2 over 2? Well, that would be at quadrant 1 and in quadrant 4. Again, I have to have the same denominators when I get these double solutions, and quadrant and cosine is positive in quadrant 4. So the idea is that we're going to be doing some factoring, setting things equal to 0, and then figuring what angles will give me the solution that I want. And there are going to be multiple angles. So far we've done 2 problems. Each problem had 4 solutions, and that was just on 1 unit circle. I would have a lot more solutions if I want to do. I could add 2 pi to all these answers to get more solutions. So when I see a problem like this, I see a problem. I see an issue. It's not equal to 0. First thing I have to do is set it equal to 0 by subtracting something over due to both sides. Then you can rewrite it. Tangent x sine squared x minus tangent x is equal to 0. What do they have in common? I see a tangent x is what they have in common. And then I could take out sine squared of x minus 1. And I could set them each equal to 0. So I have sine squared x minus 1 is equal to 0. I'm going to think about factoring that. And the other one I have tangent of x is equal to 0. Well, I just did that on the previous page. We said the solution to this was 0 and pi. There's one set of double solutions. Now when I see this guy, I'm going to rewrite him. I really see them as something squared minus 1. That's that special pattern, difference of 2 squared. Something plus 1, something minus 1. So when I factor this, I'm going to get sine of x plus 1, sine of x minus 1 is all equal to 0. And when I solve these, I'm going to move this up a little bit. When I solve this, I get sine of x is equal to negative 1, and sine of x is equal to positive 1. And when I solve for this angle, I get sine of x equal to negative 1 at the angle 3 pi over 2. And when I solve this x, when does sine equal 1? That is at the angle of pi over 2. And look at this. My double solution still has the same denominator. That's why it's going to be consistent. It's going to happen every single time. It makes my life a whole lot easier. Okay, so this next one, when I look at it, I'm like, well, I could set it equal to 0, but this one is so easy. Maybe I can just square root the thing. I get tangent of x is equal to not just the square root of 3. Whenever you square root a number, you get the positive or negative root. Okay, so when does tangent of x equal positive square root of 3 or negative square root of 3? Well, for the positive square root of 3, I get tangent of x is equal to pi over 3. And I'm going to guess 4 pi over 3 because the 2 quadrants that tangent is positive in it is in quadrant 1 and quadrant 3. So there's one set of double solutions. And for negative radical 3, I could say, oop, not x. I'm saying not tangent of x, just x. And then for this one, when does tangent of x equal negative radical 3? Well, guess what? They're going to have the same denominators because radical 3, whether it's positive or negative, all have the same denominators. I'm just going to write out pi's over 3's, and let's see. Pretty sure it better be quadrant 2 and quadrant 4 is when tangent is negative, so that's 2 pi over 3 and 5 pi over 3. Or solutions. Okay, this next one's a little bit more difficult because it seems like I have to do a bit more factoring. And I think this looks similar. So when I see this problem here, I'm going to factor it. And if you don't know how to factor, we could do our little factoring x, multiplying these two together. You get negative 2. The number in the middle here is negative 1. I want to multiply and add. So the best way to do that, I get positive 1 and negative 2 as what I get, but don't forget there's a 2 here. That 2 makes a huge, huge difference. So what happens is that I have to make this a 2x here, a 2x here, and that one looks good, but this one can be reduced to x minus 1. So it becomes 2x plus 1, x minus 1 is what I get when I factor it. Well, now I'm going to translate it, but instead of using x, I'm going to use sine of x. See, there's these signs here. So when I factor this, I get 2 sine of x plus 1, sine of x minus 1 is equal to 0. It's really the same process, but instead of having x, I'm doing sine of x. I said each of these equal to 0. 2 sine of x plus 1 is equal to 0. Sine of x is equal to, subtract 1 divided by 2. And I get sine of x is equal to positive 1. Well, when does sine equal positive 1? That's at the top of the circle, pi over 2. It doesn't have a double answer, but this one will. Well, it doesn't even matter about the negative. I know sine of x equals 1/2 when I have pi over 6. I'm going to get another pi over 6. Now I have to think about when is sine negative. Well, that's quadrant 3 and that's quadrant 4. So in quadrant 3, that's 7 pi over 6, and in quadrant 4, it's 11 pi over 6. And these are my double solutions for that one. Let's see what else I got. Let me see if I can go on. Put this up. I'm going to factor this one without making my little x, because I see 4 and a 1, so I'm going to guess 2 cosine x minus 1, 2 cosine x, cosine x minus 1 is equal to 0, and I'm pretty sure I get 2 cosine squared plus 1 at the end, and I'm going to minus 4 in the middle. But this is really just 2 cosine of x minus 1 squared is equal to 0. 2 cosine of x minus 1 is equal to 0. Cosine of x is equal to add 1 divided by 2. And what angles does cosine equal 1/2? Well, I'm pretty sure positive means I better be in quadrant 1, which is pi over 3, and I better get another pi over 3. And let's see, what are the two quadrants? Let's see, quadrant 1 and quadrant 4 is the other quadrant that cosine is positive in, so that's going to be 5 pi over 3 is my solution. So there are my double solution for that one. Okay, again, it looks like I have a problem that's not equal to 0, so I better bring it over to the other side by subtracting it. I have cotangent x cosine of x minus cosine x is equal to 0. And I do notice that there is something in common, and what they have in common is cosine, so I get cosine of x, parentheses cotangent x minus 1. Don't forget your minus 1. This is an easy one to do. Cosine of x is equal to 0. When does cosine equal 0? Well, that's the top of the circle and the bottom of the circle. Now this one, cotangent of x minus 1 is equal to 0. Add the 1 and get cotangent of x is equal to 1. Now what I'd rather do is not deal with cotangent or any of the other reciprocal properties. I'd rather flip everything. Not only going to flip the function from cotangent to tangent, I'm going to flip the number. Well, in this case, flipping 1 still gives you 1. So didn't really have much of an effect, but I still flip both the function, trig function, and the number. When does tangent equal 1? Well, that's a positive, so that better be quadrant 1, and that's going to be pi over 4, and I'm going to have another pi over 4. It's going to be in a different quadrant, but I have to have these double solutions with the same denominators. Quadrant 1 and quadrant 3 is the other quadrant that tangent is positive in. So it's 1 pi over 4, and it's going to be 5 pi over 4 as my double solutions.
Okay, it's not.
If you're watching this video, sorry about that. I lost my voice. Got to subtract 2 because it's not equal to 0. 2 sine square root of x plus 3 sine x minus 2 is equal to 0. This seems a little bit more difficult to factor than what we've done before, so I am going to set up my little, I'm going to rewrite it. Instead of doing with signs, I'm going to rewrite it as 2a squared plus 3a minus 2 is equal to 0. I'm going to set up my little x. Negative 4 is here. I'm going to multiply to that, and positive 3 is on the bottom. I'm going to add to that. Let me think. Well, I would think negative 1 and positive 4 is what I need to get what I want. And don't forget about this 2 up front. So 2x and 2x. That one's good. 2x minus 1. This one has to be reduced. X plus 2. Now I'm going to rewrite it, not with x's, but with sines of x's. 2 sine x minus 1 sine x plus 2 is equal to 0. Again, I can set each of them equal to 0. Add the 1 divided by 2, and I think we've done this earlier. Sine equals a half in quadrant 1 at pi over 6, and another pi over 6 would be in quadrant 2, and that's going to be 5 pi over 6. So that's my double solution. Quadrant 1 and quadrant 2. Now this one's a little bit more difficult. So sine of x plus 2 is equal to 0. I have to subtract the 2. I get sine of x is equal to negative 2. And when does sine of x equal negative 2? Never. Sine is stuck between the numbers negative 1 and positive 1. It can never equal negative 2, negative 5, negative 1.8, or any of those numbers in between. So you only have these two solutions. And finally, this last one, again, I see that it's not equal to 0. I'm going to do my basic algebra manipulation of subtracting things over. Sine x secant x minus 2 sine x equal to 0. I see they have a sign in common. Sine of x, parentheses, secant x minus 2 is equal to 0. So that's what I have. This part is easy. Sine of x is equal to 0. And what does sine equal 0? Well, that's at angle 0 and angle pi, which I think we've done before. This one, secant of x minus 2 is equal to 0. I will add the 2 to the other side, and I get secant of x is equal to 2, which is fine, but I'd rather not deal with it. So I'm going to flip things around. And I get cosine of x is equal to 1/2. I have to flip both the function and the number. Now this is much easier. I know x cosine is equal to half at pi over 3 and some other pi over 3. And I think about my quadrants. Cosine's positive in quadrant 1, it's also positive in quadrant 4. So my other answer besides pi over 3 is going to be 5 pi over 3. That is my double solution for that last problem. Thank you for watching this video.